Welcome to the AP Precalculus course by MathicQuest. Today's topic is 1.4 Polynomial Functions and Rates of Change. Let's look at the expression 3x to the power of 7. In this expression, 3 is called the coefficient, x is the base variable, and 7 is the exponent. The entire expression 3x to the power of 7 is called a term. Since there is only one term, this expression is called a monomial. We can create expressions with more terms by joining them using addition or subtraction. If an expression has two terms, it is called a binomial. And if it has three terms, it is called a trinomial. Now, there's no way we can memorize a special name for every possible number of terms, so once we move beyond three terms, we usually just call them polynomials. In fact, monomials, binomials, and trinomials are all types of polynomials. The names simply tell us how many terms the polynomial has. But remember, for an expression to be a polynomial, the power of the variable should be a non-negative integer. That means all of these are not polynomials because when we write them in exponent form, we do not get non-negative integer. To write a polynomial in standard form, just arrange the terms in descending order of exponents. Now in your textbooks, the standard form must be written something like this. Even though this looks complicated, it's just stating that these are the coefficients and these are the variables written in decreasing order of power. Also notice that this last term doesn't have any x. That's because it's a constant, so the power of x is actually 0 here. Now, once we have written the expression in standard form, the first term on the left is our leading term. Its coefficient is called the leading coefficient, and the value of the highest exponent is called the degree. So, for example, here the leading term is negative 2x to the 12th power. The leading coefficient is negative 2. We will also note down the sign of the leading coefficient, so that's negative. And finally, since the highest power is 12, so the degree is 12. But along with the value, it's also important to note whether the degree is odd or even. Since 12 is an even number, we will say that the degree here is even. Alright, the next topic is the extremas. These are the hills and valleys of the graph, and they come in two types, local and global. A local extrema is also called as a relative extrema, and a global extrema is also called as an absolute extrema. First, let's talk about local maximum. It is a point on the graph that is higher than all the points immediately surrounding it. Visually, it looks like the top of a hill where the function changes from increasing to decreasing. If we extend the graph, all these hills that you see are the local maximums. A local minimum is the opposite. It is the bottom of a valley where the function goes from decreasing to increasing. But what about these endpoints? Well, if the function has restricted domain, and it includes these endpoints, then these can also have local extremas. So for this graph, we get a local minimum on the left endpoint and a local maximum on the right endpoint. So till now, we know that to find a local extrema, we compare just the neighborhood points. But if we look at the entire graph, then the highest point is the global maximum, and the lowest point is the global minimum. Now, let's say we have this graph. Here these are our local maximums, and these are local minimums. We can also easily find the global minimum, as this is the least value in the entire graph. But what about the global maximum? The arrow here indicates that it is increasing infinitely. That means this function doesn't have a global maximum. Alright, now let's consider these 2 points, which are zeros of some function. Now because they are the zeros, that means the graph crosses the x-axis only through these 2 points. So it could be either like this, or like this. In the first type, we can get multiple local maximums, and in the second type, we get multiple local minimums. If we keep the graphs extremely simple, we get at least one local extrema between two zeros. Talking about polynomials, Based on its degree and leading coefficient, we can tell a few things about its global extrema. If we have an even degree polynomial and the leading coefficient is positive, so for example, let's take this function. Here the highest degree is 6. That means it's an even polynomial. And the leading coefficient is 2, so it's positive. If we plot this function, we will get something like this. You can see that both its ends are facing up. And we can clearly see from the graph that we don't get a global maximum because of these arrows, but we definitely get a global minimum. This is true for all even polynomials with a positive leading coefficient. But for an even degree polynomial, if the leading coefficient is negative, say something like this, then we will get a graph like this. Here, notice how both its ends are facing down. That means here we don't get a global minimum because of these arrows, but we do get a global maximum. And again, this is true for all even polynomials with a negative leading coefficient. This concept, however, doesn't apply to odd degree polynomials, because their graphs look either like this or this. Notice how the graph heads off to infinity in both directions. So there is neither a global maximum nor a global minimum.